All right, so this was supposed to be recorded last night during class, but I forgot to hit record. So you're getting a redo of the demo I presented last night. So this week our topic is spatial interpolation. And if you went through the Canvas modules, you'll know, hopefully by now, that interpolation is estimating the unknown values between known values. And we study it in this course because it's one way for us to create some raster data from our point data. So we're trying to fill in the blanks between all these known points. Here we're looking at temperature, or I should say here we're looking at weather stations and sort of the southern regional office of California's drought irrigation management system. I'll put the link up to the data online too. We're looking at the weather stations for and we can also then check out the temperatures for April 21st, 2019, and we can see high and low, or we can kind of see high and low temperatures throughout the region. Now, you may be have a similar problem like this with your project, that you have a point data set that has some type of value associated with it, like temperatures or soil salinity or elevation or air quality, or maybe it's a ranked maybe you ranked some variables like quality of soil, and you've given them numerical rankings, but there's some sort of value associated with these. So interpolation will help you take this and create one of those, in this example, one of those nice temperature charts you see on the evening news or online. So there are a bunch of different interpolators. The lab, you're walking through 3 or 4 of them. And there are a lot of different reasons for choosing a different interpolator. So please definitely check out the Canvas pages for some more information on what interpolators you want to use. Most interpolators give you some sort of control over some of the inputs, and some give you more control than others. One of the things you have to ask yourself when you start your project is looking at your points. And we're looking at our points here on the screen, how are they distributed through space? Because that will influence your analysis of all right, so your distribution points will help you influence what type of interpolator you use. So we can look at this example here. And we can ask ourselves the question, see if this poll will pop up for you. Nope, not that one. Let's look at these points. How do you think they are distributed? Are they evenly distributed but far apart, evenly distributed but close together, or close together in some places or far apart in others? So again, evenly distributed but far apart, evenly distributed but close together, or close together in some places and far apart in others. In this example, to me, the best description of my data was that close together in some places and far apart in others. So this leads us to some questions about some of the settings for some of our interpolators. So let's take a look at the first interpolator tool, or one of the more common ones that we start out with, which is the IDW tool. Let's search for IDW. And there's some info on IDW on Canvas that gets into the details of it, but IDW is the best example of spatial interpolation. I'm sorry, spatial autocorrelation. Spatial autocorrelation being the basic geographic principle that things close together are more alike than things far apart. So if it's raining at your house, it's more likely to be raining across the street than maybe in the South Bay or in the North County, depending on where you live. Or it's more likely, if it's raining on your side of the street, raining on the other side of the street versus Boston or New York or Denver, any place that's really far away from you. And that goes beyond just weather. It goes into a lot of demographic characteristics and most other geographic principles as well. But the basic idea behind IDW and all the spatial interpolators, to be honest, is that we can estimate the values, the unknown values between these points, because it's likely that points close together are more alike than points far apart. So our input features are going to be our points. And our, oh good, it's freezing. There we go. The next input on most of your interpolators will be asking you about the z-value. The z-value is the field that holds, if it says in the description, magnitude or value for each point. So for us, we're interested in temperature. It could be something like elevation. It could be magnitude or air pollution. It could be, concentration of disease, whatever it is, it's that value field that's telling you something more about that point than just location. So that's our Z fields, our average temperature of the day. We can change where we're saving it. Output cell size we talked about when we talked about environments. We'll come back to power. With IDW, you have a couple other search options. You can set your search radius to be variable, meaning you can go as far away from your the grid cell you're trying to estimate as needed to get the designated number of points of known values to estimate that value. So if we're looking at where the hand is, if we wanted to come up with an estimate of this grid cell here, if we wanted to find 12 points, we could just use the 12 closest points. You could tell it we are only going to search within a specific distance, so 12 points or maybe 50 miles from that known point, or 10 miles, whatever you want. You can set a maximum distance too, like we want 12 points, but don't go beyond that sort of 50 miles, whether it's variable or fixed. So most let you control, most of the interpolators let you control this thing, like the number of points. But IDW is one of the ones where you can't control that search radius. So since we decided together that my values are close together in some places and far apart in another, having a fixed search radius is not necessarily the best option, and that's something discussed in Canvas. So for us, our big thing will be changing our number of points, and we'll be changing the power in a second too. So let's go ahead and look at some of those results. All right. So here we have just that IDW that you just saw. I just stuck with the defaults, the 12 known points or sample points. We left it that 30 meter output, and we left the power at 2. So just at the defaults, it's given us a pretty good idea of temperatures. We can see hotter temperatures. We can see cooler temperatures in the green. One thing to know about IDW is you cannot estimate outside of your known values. So your highs and lows for temperature or highs and lows for elevation will match the highs and lows on your IDW output. So our lows are 46.3 and our highs is 70 something, 77.4. So none of our values for any of our IDWs will go above or below those. Now I mentioned you can change the number of points. So we can go back and do that same adjustment. You can change the number of points you want to use to influence your point you're estimating. So one of these yellow spaces or orange spaces that don't have the known value. You can visually experiment by drawing circles using the draw toolbar to kind of estimate how many you would need within 50 miles or 10 miles or what the average number is. But it's sort of a test of what you think is best. So we could change it. As you can see, I changed it from 12 points to a couple fewer to 8 points. And we can see those results here. Again, just simplifying it so we can save a little bit of time. So you can start to see some of the changes between the two, and they're a little bit slow to load. So I'll show you a PowerPoint slide of these also. So this is our default. We can see by changing it to the number of points to 8, we don't get a huge amount of difference, but you are seeing a little bit of difference out in some of the warmer parts where there fewer points to estimate. So not a huge change by reducing to 8. So is that important? I don't know. Something to think about. The other thing we can think about with our sample data is adjusting the power. And the goal, or with the power, let me open the tool back up so you can see what I'm talking about. Adjusting the power has you, this section here, it controls the significance of the surrounding points of that interpolated value. So a high power result results in less influence from distant points. Low power results more influence from distant points. So this is sort of influencing how significant spatial autocorrelation is. So the default is 2. My next example, I'm changing it to 0.5, so really reducing that power. So that's allowing us to increase the influence from distant points. So you can see if we change it here just to 0.5, and we change that number of points back to 8, we can change that here, and we can look at that, sorry if you can hear my son. We can look at that output and how that starts to change. So we can see when we change the power, we're getting what's called, we're getting what's called a smoother output. Now you may look at this and say, Rachel, there's a ton of jagged edges in here. How is this smooth? But the big change is the number of classes that you're seeing, or those bullseyes that we saw in some of our previous examples. They start to disappear. So smoothing those bullseyes out, maybe artificially they're there, or maybe they need to be there. And you can look at this and say, wow, there's some low temperatures in this area. And when we pull those out, they're still there, but maybe there being too much influence is given to those points further away. So pulling these temperatures up into warmer, making it warmer in this area than it necessarily should be. So maybe the power isn't really the best option here. I also did an example where I changed it back to 12 points, search points, instead of a control points of 8, and moved it back to 12 and left the power at 0.5. You can see again that smoothing, really decreasing this cold spot, its presence there. So again, not smooth, like you're still gonna see the jagged edges. And then the last one I did was just changing that, leaving the power at 2 and changing the search to 5. So instead of looking at 8 or 12 points, we're looking at a lot fewer. We'll see those results in a second when it loads, maybe. Maybe those are the results there. So let's go back to our PowerPoint slide and you can kind of compare those. So we can go back to our default with our 12 points, no power adjustment, 8 points with a power adjustment, 8 points, but changing the power to 0.5. So increasing that smoothing, increasing influence of points further away, changing the points back to 12 and changing that power. So again, see the smoothing, points further away, more influence. So we're really seeing the loss of let's get rid of this. You can see it, whatever. You can see the influence of points further away they're having on these cold spots. We're sort of losing those. And then just going down to 5 points, we can see what that does. I don't know if it has that much influence. I kind of just like it at the 12, but then it has these weird spots here. So we'll see, anyway, that's IDW. And we'll get to those questions I have at the end, like, what does this mean? Which is the best one in a second. The second demo I did, or that, I mentioned that we're looking at several different interpolation tools. And one of the other things you may have caught that I said was that in interpolation and in IDW interpolation, it can, oops, let's turn some of these outputs off. Spoiler. Okay, in your interpolation, IDW interpolation, you cannot, interpolators will not, let me start again. With IDW, your output server, oh my gosh, one more time. With the IDW interpolator, your output surface will not have estimates above or below your known values. That's one of the benefits of IDW. It's controlling how much spread you get in your data, but you may have something like temperature and you're thinking, Rachel, it's likely that there were temperatures higher than 77, or maybe there was a temperature lower than 46 or 43, whatever it was last April. How does it take into consideration those values? Or maybe this isn't the best tool. Well, you know, another tool you can use is Spline. So IDW and Spline are two of the best tools to start with because they require the least amount of knowledge of some of the more sophisticated settings and more a higher level of geostatistical analyses. So great place to start. So if you know you have values above or below, you could look at Spline. So here we can see just the, let me open the tool first. That will make more sense. So here we can see our tool. It's interpolating a surface from points. The resulting smooth surface passes exactly through the input points. So that means that any of your estimated values or any of your known values will have the known values on the output surface. Same thing that we saw in the IDW with the first two is our input features, and then the Z field are those values you want to put on that raster surface. And if we just leave everything at the default, the output cell size, number of points, not changing anything, we end up with our first surface here. So one of these settings, so you can see it looks quite different than the IDW. One of the settings on that spline tool, where is it, is this option, the spline type. So spline is sometimes called rubber sheeting because you are, the idea is you're basically taking a rubber sheet of data, if you think about resistance bands for exercise, and fitting it through all of your known points. So it's the flexibility or the tension in that rubber sheet or rubber resistance band. That's what the two options here, the spline type, regularized or tension. With regularized, you're using a resistance band with lower levels of resistance. So it's more like floppy, more free flowing. And you can see from these values in the output, we have values that are quite a lot lower than our known low point, which is 46, and quite a lot higher than our known high point, which was 77. So you may think to yourself, well, Rachel, we probably have values above or below 46 and 77, but I don't know, 112 seems really high. Maybe that's too high. So you could then go back and choose your tension method. And you could change that to a rubber surface or resistance band that has a rougher, a more tension in it. So it's a stiffer rubber sheet. It's a band that requires more muscles to sort of flex around. It will not have, its output values will have, will maybe above and below your known values, but it keeps that line a lot closer. And you can see on Canvas, there's a great graph that sort of demonstrates this that I should have pulled up for you. But we can see just with those defaults, with the tension method, our low points is 45, our high point is 84, a lot closer to our original low points of 46 and 77. So it still gives us some variation that there might be some high points and there might be additional low points, but it's not the 112. So it might be a good place to start. The other one that I mentioned was, or I should say, also with spline, you can change the number of points. So we can say like maybe that tension method works a little bit better for us, but we want to try to use fewer points. We can go ahead and try that. We can see here the output for that spline tension method with just 8 points. And you can see how that changes from the regular tension. Maybe. All right, so you can see, oh, well, let's turn this one off because we don't need it. So our original spline tension method, we can turn it on. We can turn on with the 8 points and start to see how that changes our results a bit. Oh my goodness, this is so slow to display, and I don't have this as a slideshow, which would have been smart. But you can start to see how that shifts slightly when we're using fewer points to estimate the points in between. So it's your basic just demo of 2 different interpolation tools. The lab will walk you through some of the different, a couple other different tools. The other thing I showed last night was interpolation tools are great if you want to know the values or use the values of these points to estimate the surface. If you, the lab is also going to walk you through a couple tools for density and a couple tools to validate your spline outputs. I haven't gone through that, but there's the examples in the lab on how to assess your interpolators for which one's the best. But anyway, if you wanted to just know density, maybe you just wanted to know the density of weather stations in Southern California, or you wanted to know the density of bus stops or crimes or whatever it is. Don't use an interpolator, use one of the density tools. So you'll get a look at the point density tool in this lab, and you can see the output here once it loads maybe. That gives you sort of that different overview. So instead of telling you values, it's just showing where concentrations of points are. So the darker areas are where the overlaps are. Those are where there can be, greater concentration of crimes or whatever your values are. So those are the things that I demoed last night. I have to put up a demo on cross-validation, but keep an eye out for that.